this slide about the overview and the specification of the existing design general bearing. Before we go through, I will explain about the primary function of the general bearing. The general bearing is to manage the shaft vibration and prevent the excessive displacement caused by hydraulic force. For the selection design for my team to do this research is about I select the sleeve bearing with fully grooved water lubricated. For the material, I select the lignum vitae, which is well water lubricated. For the key operating characteristic, I choose load minimum 0.3 megapascal and the shaft diameter is 600 mm and the rotational speed about 200 rpm and the diameter clearance is 0.2 mm. For the performance and delimitation, for the lubrication challenge, water is normally have lower viscosity compared to the mineral oil. So, water naturally lower the potential thickness of the lubricating film. So, the metal to metal direct contact will happen sudden if the minimum film thickness is too low. For the testing result, at the 0.3 megapascal, it show the non-uniform pressure because the journal operate with high eccentricity, causing the uneven pressure distribution across the pad. And the second, the uneven load sharing because the radial load is heavily concentrated on one dominant pad only, rather than evenly distributed among all pads. And then the critical output value, which is from the paper, the minimum water film thickness is 9.6 micrometer, which is extremely thin compared to the mineral oil. And then the eccentricity ratio is 0.9, and then the attitude angle is 0.904 degrees.
So next we will discuss about the root cause of failure, which is divided into two main points. The first one is about the mechanical and design faults. So the first one is the shaft misalignment, which is the most significant phase caused by assembly or foundation shift, results in linear load capacity decrease. Next, installation and machining, which is about the faulty machining leads to thermal stress during mounting, causing material pre-damage. And the third one is the isothermal assumptions, where ignoring shear generated heat can lead to unsafe design margins and loss of stability. And finally, inherent viscosity limits, where water's low viscosity creates thinner films, reducing load carrying ability at low speeds. The second one is about the operational and environmental, where the first one is about the lubricant contamination. Seal and debris cause abrasion or scratches, degrading the hydraulic film integrity. The next one is about the tension regimes, which is about the stop operation shift lubrication from hydrodynamic to boundary, causing metal to metal wear. And the third one is about the extreme hydraulic loads. Unit weight and instance forces can exceed bearing pressure, causing a film failure. And finally, about the environmental corrosion, water and humidity degrade the structural integrity of critical bearing components. So finally, we will discuss about the influence on the lubricating performance. The first effect is about the viscosity loss, where heat from friction thins the lubricant, causing hydrodynamic pressure to flatten, where the peak pressure decrease near center and up to 60% load capacity reduction and critical threshold around 109 degrees Celsius. The next one is about the contamination. The particles, which is silt and sand, disrupt the slippery cushion of the lubricant layer, which cause scratches and that prevent the uniform film. Contact generates localized heat and results in alloy wiping or melting. And finally, the vibration, water film failure directly leads to significant axial instability, and no characteristic frequencies manifest as anomalous energy, and finally detected via anomaly energy data.
Okay, we continue with the through system optimization. Require an integrate overhaul of geometry, material and lubrication. For the first one is for the geometry is adjusting the physical dimension, specifically expanding the radial clearance and testing distinct length to diameter and over the ratio to manipulate the bearing pressure. And the second one is the lubrication for maintaining environmental safety with water, but upgrading the delivery and purity to maintain stability at 6.28 mm per second sliding velocity. And for the third one is material, which is we need to move it away from inconsistent traditional hardwork, a modern engineering composite design implicitly to tolerate low viscosity environment. For the next one is the upgrading to continuous clean filtration and resilient polymer composite. And for the material upgrade, we choose polymer composite over lithium vitate. And this is because to replacing lithium vitate with a water compatible polymer composite is eliminate material inconsistent, provide superior corrosion resistance, and dramatically improve wear resistance against minor abrasive particles without requiring surface coating. And for the second upgrade is the lubricant upgrade, which is from the raw water we use the clean filter water. It's because we can reject oil and grease to maintain environmental safety, which is zero leakage risk. Instead, we implement a continuous clear filter water supply. This actually flush the draft bearing groove, cooling the system and preventing seal and sand from initiating abrasive wear. Okay, for this one, we need to testing the three distinct geometry profile to optimize load distribution and film thickness. To improve film formation, we double the radial clearance from 0.1 mm to 0.2 mm. With the shaft diameter fixed at 600 mm, we analyze the length, diameter, L over D to configuration to balance bearing pressure against alignment sensitivity. All case share calculate Sommerfeld number of 0.25. For the case 1, which is valent, we choose length 300 mm and L over D is 0.5, and we expand 0.2 mm radial clearance. And for the case B, which is a bit long, for the length is 600 mm, for LV is 1.0, and we expand 0.2 mm radial clearance for the case B. And the next one is case C, which is a bit short. The length is only 150 mm, and L over D is 0.25 mm. Okay, we continue with the next slide.
Now I will presenting the results of our Raimondi and Boyd modeling, focusing on three bearing geometries with different L over D ratio. Starting with case B, L over D is 1.0. The balance geometry at 1.0 we found eccentricity is 0.41 and attitude angle is 61.9 degree. As for the friction variable, it is 6.6, while for the flow variable is 4.0. This case represents smoother operation with reduced eccentricity, though it sacrifices some load capacity. As for the case A, with L over D ratio is 0.5, the eccentricity rises to 0.64. However, for the attitude angles, it lowers to 44 degree. As for the friction variable, we found it is 5.5 and the flow variable is 5.0. This geometry offers a good compromise, higher load support compared to case B while maintaining balanced lubrication. Lastly is case C with L over D ratio of 0.25. Eccentricity we found is the highest among all, which is 0.82, but with the lowest attitude angle of 31.5 degree. As for the friction variable, it peaks at 8.0 and the flow variable is around 5.6. Thus, this case shows instability and higher friction losses despite thicker film formation. In summary, the modeling reveals distinct behavioral profiles such as case B, which is smoother but less load bearing. Next is case A, which is it balances stability and lubrication, and lastly is case C, which increases friction and instability. These trade-offs highlight how the choice of L/D ratio directly impacts on the bearing performance in turbine and lubrication system design.
Okay, so this is the phase optimization calculation for the three cases, which is, as we can see here, the minimum frame thickness is for the case A, which is at 0.2921, and the lowest power loss is actually at case C is 0.906, and the highest minimum thickness is also at the case C, which is 0.3398, and the lowest power loss is actually at 2.488. So even though the case C has the lowest power loss, but when we want reduce the friction and also want have the stability, the case B is actually has a balanced result, which is it has the moderate power loss, and also it also has the moderate frame thickness. Okay, so this is the justification for the design selection, as we mentioned in the previous slide, which is we have three justification, which is first is this case has actually the optimum frame thickness, so that we could prevent the abrasion and also the surface wiping. And the second is actually low power loss, so even though it does not have the lowest power loss in the calculated, but it actually has a low abrasion and heat generation rate, and it's also efficient for hydroelectric, so the value is acceptable. And for in terms of the geometric stability, so since we increased the radiant clearance by 0.2 millimeter, and it could allowing for the forming of stable hydrodynamic layer for water, and this also helps the hydroelectric bearing is suitable for the long-term operation. So in conclusion, we have three conclusions for this topic, which is first is actually the redesign optimization, where we maintain the water as the eco-friendly lubricant, and we also increase the radial clearance, which is at 0.2 millimeter. And in terms of the material, we replace the original material, which is the lignum vitae, to the polymer composite material. And in terms of the performance result, we choose the L/D equals to 1, since it has the minimal friction and also it has a low power loss. And in terms of the overall impact, when we choose the low power loss and low friction and also has the high stability, we could enhance the turbine operational, and also we could reduce the maintenance cost for this design. So in overall, this is the recommendation for the future work for this project, which is we have the continuous water filtration system, so that we could install the industrial grade filter in the future. And the second is in terms of condition and vibration monitoring, which is we could install the sensor to monitor the monitoring, and also we could have a precise shaft alignment, so that we could ensure the exceptional precision during site assembly. So that's all from us. Thank you.